All right, so we did some stuff to introduce this idea of confidence intervals and margin of error. And so we're going to continue with this of confidence intervals for the mean when our sigma or standard deviation is known. All right, so find confidence interval for the mean when standard deviation is known, and determine the minimum sample size for finding a confidence interval for the mean. So several definitions here. A lot of these we've talked about. Inferential statistics involves using a sample to draw conclusions about a population. So now we're getting into some real interesting stuff and be able to do stuff with our data. Parameter is population. Mean statistic is our sample mean. And then best point estimate is a specific numeric value estimate of a parameter. All right, so those three things are ones that we worked on the other day in class. So as we look over here, an interval estimate of a parameter population is an interval or range of values used to estimate the parameter. All right, so let's look at an example here. In an interval estimate, the parameter is specified as being two values. The average age of all students might be 21.9 to 22.7. This could also be written as 22.3 plus or minus 0.4 years. Either interval contains the parameter or it does not. A degree of confidence, usually a percent, can be assigned before an interval estimation is made. This is where we did that 95% confidence in class the other day. And that's our most common one. Here for the question number one, though, we're going to use 99%. And so if you desire to be more confident, say 99%, would the interval get bigger or smaller? Well, as we saw, as we increase our confidence, we have to increase our interval. And you can see here from our normal distribution, right, 99% is far larger than our 95, and then 99 or 90 is even smaller than that. So what is the trade-off to be more confident? Well, your interval gets larger. All right, so to be more confident, the interval has to get larger. So a confidence interval is a specific interval estimate of a parameter. An estimate is a key phrase of the parameter, so our true population value. Determine by using a sample, all right? And so that's a little bit of work we did yesterday with that chapter 6 previous test. Okay, this is our formula as we've talked about, right? This is our sample mean or point of estimate. Okay, again, just our sample mean. And then that is our margin of error. All right, because we add or subtract that, and that gives us then our interval for our confidence. And so our margin of error is the maximum likely difference between the best point of estimate and the parameter. All right, and so then what we're looking for in this sense, all right, is our ZA over 2 symbol is the area in both tails combined, so that area and that area. So if we're looking at a 90% confidence, that means there's 10% data outside, and so therefore there has to be 5% on this side and 5% on that side. All right, so using the ideas, we're going to find the z-score corresponds to 40%, so that middle 40, the middle 78, and the middle 96. And we can use our technology to do this. So we got Staplet. All right, we'll go here. Our mean, because we're normalizing this, is going to be 0. Our standard deviation is just going to be 1. We're going to calculate a value corresponding to an area. So we get a normal distribution there with 0, 1, 2, 3. Everything's been standardized. We want the central portion. And within that central portion, I want 40%, which we convert to a decimal as 0.4. And we calculate that value. And it gives us our range. And we're just going to do the positive side of that. So 0.524. And then for 78, we just change that 0.4 to 78 and calculate that value. And we get negative 1.227 to 1.227. We'll just write that positive value down. And last one, 96%. And again, you can see that the tails are the empty, so we're shading in that middle part, and what's left on the outside, okay, is the area that's outside of that. So there's 4% left outside that, or 0.2 on each side, and that gives us all the way out to a z-score of 2.054. Hey, a couple quick assumptions. Samples must be randomly selected, either n is greater than or equal to 30, or the population is normally distributed if it's less than 30. We've talked about that previously before. All right, let's look at 4. A researcher wishes to estimate the number of days it takes an automobile dealer to sell Chevrolet Aveo. A sample of 50 cars, so greater than 30, had a mean time on the dealer's lot of 54 days. Assume the population standard deviation to be 6 days. Find the best point of estimate of the population mean and the 95% confidence interval of the population mean. So let's write down some of the information they give us. So n is 50. Our sample mean was 54. Standard deviation was 6. And we want a confidence interval of 95%. So our point of estimate is already given to us. All right, point of estimate is just our sample mean. So it's 54. And then we're looking a little sketch here. All right, we want 95% in between there. So it can take that mean, all right, was 54. Standard deviation is 6. And we want 95. And that gives us 1.96. So we'll bring this back, write that down over here. Okay. And then, so that 1.96 helps us with, remember this formula all the way up here. So our sample mean minus z alpha 2, standard deviation over square root of n. It's going to be less than our mean and you don't have to write this down every time, just writing it down for this first time for you. So let's plug in our information. So our sample mean was 54 minus, that's our 1.96, our z that we got. And then our standard deviation is 6 over the square root of 50. And then, nice thing if you're kind of doing this here on your iPad, and you move that over, and just make sure you put plus on there. Simplify that out, and we get 52.3 to 55.7. And you write something like with 95% confidence and a sample size of 50, the number of days a Chevrolet Aveo will sit on a lot on average 52.3 to 55.7 days.